Ever pondered over the fascinating secret behind the opalescent glow of a pearl or the stability of milk? The answer lies in the world of colloids. Welcome to an adventure that takes us into the microscopic realm, where particles dance in a mesmerizing ballet of interaction and influence. This is the realm of colloids, a unique mixture where tiny particles of one substance are dispersed, but not dissolved, within another substance. These aren't just scientific curiosities. They're all around us, playing pivotal roles in our daily lives. That luscious ice cream you enjoy on a hot summer day, the cosmetics that enhance your beauty, the ink that flows from your pen, and even the cells in your body all owe their existence to colloids. This is a world where the properties of substances are dictated not just by their chemical composition, but also by their size and interaction with their surroundings. So, are you ready to dive into the captivating world of colloids, where size does matter? In the spectrum of matter, colloids hold a unique position with their intriguing types. Colloids, in their simplest definition, are a mixture in which one substance of microscopically dispersed insoluble particles is suspended throughout another substance. Now, let's dive into the myriad types of colloids that exist. First up, we have aerosols. These are colloids that have particles of liquid or solid dispersed in a gas. Think about the mist from a spray bottle or the smoke from a campfire. Both are examples of aerosols, where tiny droplets or particles are suspended in the air. Next, we have sols, which are solid particles dispersed in a liquid. The paint you use to colour your walls, that's a sol. The solid pigment particles are dispersed in a liquid to create the paint. Then there's emulsions, where we have one liquid dispersed in another liquid. Picture the vinaigrette for your salad, where oil is dispersed in vinegar. That's an emulsion for you. Gels are another type of colloid, where a solid network extends throughout a liquid. Jello, a favourite dessert for many, is a perfect example of a gel. Moving on, we have foams, which are gases dispersed in a liquid or solid. A frothy cappuccino or a marshmallow both are examples of foams. The tiny air bubbles are dispersed in the liquid coffee or the solid sugar network. Lastly, we have solid foams, where a gas is dispersed in a solid. The classic example of this is a sponge. The tiny air pockets dispersed in the solid make it light and able to absorb liquids. And then there are solid sols, where solid particles are dispersed in another solid. Alloys like bronze or steel fall into this category. The different metal atoms are dispersed throughout each other to create a new material with unique properties. As diverse as they are, all colloids share certain characteristics that make them stand out. But that's a topic for our next scene. Stay tuned. The charm of colloids lies in their distinct optical, kinetic, and electrical properties. Let's start with the optical properties. You know how a beam of light can be seen when it passes through a dusty room? That's an example of the Tyndall effect, a phenomenon where light is scattered by particles in a colloid or in a very fine suspension. Picture a disco ball spinning in the middle of a dance floor. The light hitting the mirrored surfaces is scattered in all directions, creating a starry night effect. That's essentially what's happening on a microscopic level in a colloid, with particles playing the role of the disco ball. Moving on to kinetic properties, let's talk about Brownian motion. This is the random zigzag movement of particles in a fluid due to continuous, unpredictable collisions. It's a bit like watching a pinball bouncing around in a pinball machine, constantly changing direction due to hits from the flippers and bumpers. In the case of colloids, the continuous movement of particles prevents them from settling down due to gravity. So, in essence, Brownian motion is a kinetic property that contributes to the stability of colloids. Now let's delve into the electric universe of colloids. These tiny particles often carry an electric charge, which significantly influences their behavior. This is where charge stabilization comes into play. Think of it as a group of people in a small room, each holding a magnet with the same polarity. The similar charges repel each other, keeping everyone evenly spread out instead of clumping together. Similarly, in colloids, the like charges on the particles create a repulsion force, preventing them from aggregating and keeping the system stable. Now, you might wonder, where does this charge come from? Well, it's all about the interaction between the particles and the medium they're in. Sometimes a layer of ions from the medium adsorbs onto the surface of the particles, giving them a charge. Other times, the charge may be due to the ionization of groups already present on the particle surface. But the story of electrical properties doesn't end there. Most colloidal particles actually have something called an electrical double layer. Picture a planet with two shells around it. The inner shell is tightly bound to the planet, while the outer shell, though still attracted to the planet, is more loosely bound and can somewhat move around. In colloids, the planet is the charged particle, and the shells are layers of ions. The existence of this electrical double layer is crucial for the stability of colloids. These properties not only define colloids, but also play a key role in their stability. So the next time you encounter a colloid, remember, there's a whole universe of optical, kinetic, and electrical properties at play. To understand the stability of colloids, we need to peel back the layers, specifically the electrical double layer. Imagine a colloid particle, like a tiny planet, enveloped by two layers of electric charge. This is the electrical double layer, a key player in colloid stability. The inner layer, also known as the stern layer, is a thin sheet of ions tightly adhered to the colloid surface. The outer layer, or diffuse layer, consists of a cloud of ions loosely associated with the colloid particle. The interplay between these two layers creates the electrical environment that influences how colloid particles interact with each other and their surrounding medium. Now let's talk about potentials. The Nernst potential is an important concept that describes the electric potential difference across cell membranes. It's essentially the voltage required to prevent net diffusion of an ion across a membrane. It's like the energy gatekeeper, controlling the passage of ions in and out of the cell. On the other hand, the zeta potential is a measure of the magnitude of the electrostatic repulsion or attraction between particles in a colloid. It's like the social director of the colloid world, determining whether particles will clump together or keep their distance. A high zeta potential means particles will repel each other and remain dispersed, leading to a stable colloidal system. Conversely, a low zeta potential increases the risk of particles coming together, leading to aggregation and possibly the collapse of the colloidal system. So, the electrical double layer and these potentials aren't just abstract concepts. They're the invisible puppet masters, pulling the strings behind the scenes of every colloid. They dictate how particles move, how they interact, and ultimately how they contribute to the stability of the colloidal system. These potentials are the invisible forces that keep the colloid world in balance. Understanding them is like unlocking the secret language of colloids, giving us the power to predict, manipulate, and even create new colloidal systems. In the realm of colloids, equilibrium is not just about balance, it's about Donnan membrane equilibrium. This intriguing concept is a pivot point in the colloid universe, and today we're going to demystify it. Imagine a semi-permeable membrane separating two solutions, one with a colloid and the other with an electrolyte. This membrane allows the passage of some ions, but not all. The Donnan membrane equilibrium comes into play here, as a fascinating game of balance that unfolds. The colloid ions, unable to cross the membrane, create an imbalance. But nature loves equilibrium, so the electrolyte ions rush in to restore the balance. However, due to the selective nature of the membrane, not all ions can cross over, leading to a difference in ion concentrations on either side. This difference, or the Donnan potential, is the driving force behind many biological and industrial processes. For example, it plays a crucial role in maintaining the ionic balance in our cells, affecting everything from nerve impulses to muscle contractions. But it's not just biology. In industries like food processing or wastewater treatment, understanding and manipulating the Donnan membrane equilibrium can make processes more efficient and sustainable. So while it might just seem like a fancy scientific term, the Donnan membrane equilibrium is an unsung hero, underpinning so much of what we see and experience every day. In the dynamic world of colloids, the Donnan membrane equilibrium is the anchor that maintains order. From the glow of a pearl to the stability of milk, we've unraveled the mysteries of colloids. We've delved into their diverse types and probed their optical, kinetic, and electrical properties. We've journeyed through the electrical double layer and understood the Nernst and zeta potentials. Finally, we've demystified the Donnan membrane equilibrium, a concept that contributes to our understanding of this fascinating world. Subscribe for more because you won't find me later. Stay curious and keep exploring the incredible world of colloids.